Hi, everyone. My name is Joe DeMartini. I'm a PhD candidate at the University of Maryland, College Park, working under Professor Derek Richardson. Today, I'm going to talk to you about modeling high-porosity regolith on low-gravity planetary surfaces. I want to apologize in advance. I meant to be there in person, but I'm having a tough time getting over COVID, so I'm going to try to keep this brief. A little bit about the surfaces that we're investigating in our study. Mostly, we're looking at the surfaces of rubble pile asteroids. These are gravitational aggregates of blocks left over from collisions in space, mostly held together by self-gravity and with regolith ranging from dust to boulders in size. We've been very close to 3 asteroids in the past 2 decades. Itokawa, which has about 40% bulk porosity on the surface. What I mean by that is a macro porosity, that's void space in the entire asteroid, which is measured as an underdensity compared to the constituent rocks. So about a 40% bulk porosity on Itokawa, and this is a patch of its surface, about a 50% bulk porosity on the asteroid Ryugu, target of Hayabusa 2, and also about a 50% bulk porosity on Bennu, target of the OSIRIS-REx mission. The interesting thing, however, is that the porosity at the surfaces of these asteroids are estimated to be even higher than the bulk porosity of the asteroid as a whole. If you listen to Kevin Walsh's talk yesterday, you'll know that the OSIRIS-REx touch-and-go sample acquisition mechanism met almost no resistance as it penetrated the surface of Bennu. And they estimate that the surface at Nightingale Crater has a 70% or possibly even higher porosity. And so how can we make such fluffy regolith? That is the question that we're trying to answer. We do this with simulations. The code that we use is PKDGrav. It's a parallel n-body gravity tree code, which uses a soft sphere discrete element method to model contacts between spherical particles by allowing a slight interpenetration at the point of contact, with a degree of interpenetration mediated by a restoring spring force, with spring constant akin to a material stiffness. Recently, with PKDGrav, we've become able to accurately and quickly simulate with what we call aggregate particles. Look for a paper that we've got in preparation right now, coming later this year. We call these ags, and basically what we do is glue a couple of spheres together into an irregular shape. This lets us keep the simple gravity calculation and collision detection algorithms of using discrete spheres as constituents, but also model shape effects that are important in granular interactions, like increased shear strength. The last bit of background that I want to give is on typical porosity of well-packed granular media. So the hexagonal close pack, which you can see here in a model of Apophis from my 2019 paper, is the most efficient packing distribution of monodispersed spheres. It has an analytically calculable porosity of 26%. That's the bulk porosity of this asteroid is 26%. You calculate it analytically. It's also the simple cubic packing distribution, where you have a cubic lattice, sort of like this cube-shaped aggregate here, where you put one sphere at the corner, at each corner of the cube-shaped lattice. This also has an analytically calculable 47.6% porosity. I'm going to show that in simulations with randomly packed polydispersed spheres, that's spheres of different shapes packing randomly, not in an organized manner, we get about 40 to 50% porosity. And when we have systems with randomly packed mixed aggregates, so irregular shapes, we can get 50 to 60% porosity with little else going on in the system. The way that we estimate the porosity, essentially we start with a system of particles and we draw a concave hull around it. We do this with the alpha shape package developed by Kenneth Bellick, available for free. This draws the alpha shape or the hull with vertices at particle centers for the exterior particles. We move those vertices to the particle edge radially from the center of mass. We account for sphere-sphere overlaps. I mentioned that our model allows spheres to interpenetrate slightly, so we need to account for that volume. And we're in the process of accounting for volume exterior to the hull. So as you can see, bits of these spheres at the edges are sticking out, and that creates an uncertainty for us as well. We've not yet implemented the method of accounting for that, but we're very close. Then essentially all we have to do is calculate the porosity, which is 1 minus the total volume in spheres, accounting for these two things, divided by the volume of the hull itself. We can visualize the system after the fact, and the code for the visualization was developed by a community college student who I worked with not too long ago, Autumn Jackson Bartholomew. This was essential in debugging the code for this, so wanted to give her credit there. Oops. So let's look at how we're actually checking to make sure that we're calculating this accurately. We use a small system of essentially spherical, hexagonally close-packed particles. This is about 30 centimeters across, particle radius about 1 centimeter. The theoretical porosity for a hexagonally close-packed system, as I said before, is 24%. Here we calculate about 27.8% porosity. So we're overestimating porosity, and this is because our alpha shape, our concave hull, does not perfectly fit the shape here. We have these areas where we're not tight to the shape of the body. So that's something we need to be careful of. Over here, we look at the simple cubic packing distribution for a very small system, just the 1 cubic aggregate. And the theoretical porosity, again, is 47.6. We calculate a way underestimate, a negative 6.7. So this system is being calculated as overpacked by these spherical grains. And that's because we have them sticking out too much from these edges, and it's calculating way too much volume in the spheres as compared to the hull. So we need to be careful of small systems, and we need to be careful that we're packing, that we're generating our alpha shape tight to our system of particles. So let's look mostly at large systems here. These are 2 random polydispersed packed spherical packing distributions. This one is spheres with radii ranging from 6 to 18 centimeters packed in a microgravity environment, so a uniform microgravity plus self-gravity. The porosity that we get, we can see a fairly tight mesh around the particles here. The porosity that we calculate is about 45%. This is also a randomly packed spheres with radii ranging from 2.4 to 7.1 meters in radius, settled under self-gravity. And so no uniform gravity here. And the porosity for this whole asteroid is about 47.3%. Not a bad bulk estimate. Now let's move on to our irregular shapes. Most of the systems that I'm going to show you here were prepared similarly. They're settled under uniform lunar gravity. The particles also have self-gravity. We use uniform symmetric shapes. So in each of these models, only the shape shown on the side here is the shape that is actually in the system. This is all tetrahedra packed together. This is all dumbbells like this. The spherical constituents, the spherical constituent particles for these aggregates are 1 centimeter in radius. And unfortunately, there's a large particle embedded in all of these, just where the break in colors is. We used what we had at hand to prepare these systems. These are preliminary results, but because they're all prepared the same way, the comparison is still relatively valid. What we're finding for these tetrahedral packing and the dumbbell packing is actually relatively similar porosities as the random spherical packing, about 45% porosity. But when we move to stranger shapes, cube-shaped aggregates, these diamond planar shapes, or these 4-particle rods, we get 50% porosity, 55%, or even 57% porosity, as these things show how much more difficult it is to pack them together in these tight volumes.
You have 1 minute.
Thank you. We also have a system of mixed aggregate shapes. We put all 5 of those shapes I showed before into one system, and we get about a 53% porosity. We also have asymmetric shapes. So these are sort of our symmetric aggregate shapes, easily prepared. These are based on ellipsoidal axis ratios. Particles inside are half a centimeter radius and packed in a hexagonal close pack distribution. So they're the particles that make up an aggregate are packed very tightly. The aggregates themselves are a range of shapes and sizes. This is a microgravity environment, again, with self-gravity between the aggregates. And the size of the aggregates ranges from 1 to 10 centimeters in radius, but we still calculate about a 53% porosity. I don't have a ton of time to go over my conclusions, but essentially we're finding systematically a higher porosity in systems with randomly packed aggregates than with randomly packed spherical particles, the size distribution. But we still need more. We only got up to almost 60% in our highest porosity system, and that's not enough to match the surface porosity measured on the Nightingale crater. venue. Thank you very much. Happy to take questions.
Thank you.